I'm gonna mute real fast. you hit the go button? What's the deadline, midnight? Midnight on March 15th. God, that was hard to do. I mean, it's not our best effort, that's for sure. Yeah. Hello. Pick a seat, any seat.
Yeah, I mean, I like the
Okay.
program. Wish I could have been here sooner.
Good evening. Welcome to Juan Catholic High School for the first of what we hope will be annual Science and Society seminars. My name is Chris Long. My last job at Juan was I was the athletic director up until last May. In a prior life before that, I was an English and history teacher. And I will be your master of ceremonies tonight. For those of you who may have seen the press releases and were expecting Mary Nichols, and I've already keenly observed I am definitely not Mary Nichols. Mary's much taller than I am. Seriously, Mary really wanted to be here tonight, but it turns out she has a job, which I do not. And her employer actually expects her to work, which I did not, even when I did have a job. The birth of this program came about on a hot day last summer when Juan Diego's principal, Dr. Daly Colosimo, was sitting in his office doing what he does best, staring out the window and thinking. When he realized that he could barely see the St. John the Baptist Parish about 100 yards away in the smoke-filled air from giant wildfires, not in Utah or even in Nevada, but from California. Being the astute observer he is, Dr. Colosimo thought, this is a problem. A big fire in California big enough to cloud the air in Utah. And there it was, the birth of the idea, fire in the West. Dr. Colosimo and myself are well into our 60th decade of life in Utah, and until recently something like that had never happened. But it is happening with alarmingly increased frequency, as we saw in Colorado last month, in places that were previously thought to be safe. These are not your father's forest fires. Smokey the Bear did not see this coming. So that's what tonight's program is about. What has changed in the West that has caused this historic change in wildlands fire frequency, size, and intensity? What does it mean for our futures? To address these questions, we are incredibly grateful to have with us tonight two fire experts. Almost Dr. Dan Menes, chemical engineer in the United States Forest Service, and Captain John Slater, fire management officer for United Fire at Camp Williams Military Base. I'm proud to say that both Dan and John are Catholic school graduates, who many years ago may or may not have spent time in Gym 22 at Judge Memorial, dodging chalk and erasers thrown by an overly enthusiastic English teacher. Pretty sure the statute of limitations was run out on that before I mentioned it. But again, we are very grateful to Dan Menes and John Slater for giving their time and expertise. Gentlemen are right here. Pat Bayer and Mrs. April Vanderslice, who did all the heavy lifting on this project tonight. With no Pat and no April, there would be no program. Thank you so much, Pat and April. So thank you for being here tonight, and I will get out of the way, and our first presentation tonight will be by almost Dr. Dan Jimenez. Thank you.
Thank you. Yeah, I would like to extend a thank you as well for the invite to Juan and Judge staff for allowing me to be here. My name is Dan Jimenez. I'm pretty excited about this fire and water event. It's something I'm pretty passionate about. I spent a career working for the Forest Service. I grew up in the Valley. I went to St. Ambrose. I graduated from Judge in 1986. I, from there, pursued a chemical engineering degree at Rutgers. I took a job in Washington at a national lab and got a master's in civil and environmental engineering. And then I heard about an opportunity with the Forest Service in Missoula, Montana, to work at a fire science lab, which was a bit of a detour from what I'd been doing. But the excitement about living in western Montana and my lifestyle at the time, just the intrigue was too great. And I found myself moving to Missoula, and for 25 years I've been at this research facility, and I'm learning every day. It's an incredible place. The work we do is very inspiring. I work with fire scientists, climate scientists, plant physiologists, fire ecologists, and our overarching goal is really to make firefighting safer, manage our habitat, protect people, save taxpayer dollars, and think about how this is all changing as our future progresses. You know, since I was asked to do this presentation about 5 months ago, you know, I like to read anyway science articles, and I couldn't help but think, oh, this would be a good headline to add to the conversation. This would be a good headline. Before I knew it, I had more headlines than I could fill my whole talk with headlines. But this is a common one. Fires around the world have grown wildly. You know, what is normal? And what is the new normal? And what are we, from a wildfire management perspective, doing to factor in this new normal that we're seeing, these extreme fire events? All right, is it getting warmer and drier? And how is the climate change factoring into our fire seasons? You know, every year we seem to be setting records with temperature and drought. Montana had fire in December this last year. That's never happened in the 25 years that I've been there. You know, the mega drought is continuing. Locally, Salt Lake is shrinking. Lake Powell is shrinking. The Winter Olympics may not have snow. I grew up in this valley. That's very dear to me. I know what it means to you and it means to me to lose snowpack. What are the impacts of that? So the headlines are suggestive that something's happening. Really, is it just happening here? In 2016, Canada had one of its largest fire seasons ever. Towns were evacuated, properties were lost, fatalities. Greece in 2021, massive property damage, massive fire on a scale that had not been seen throughout the Mediterranean. I'm sorry if print's small, but what I will do is pointer will help. So in 2020, the Amazon had record-breaking fire. 2020, Australia had record-breaking fire. We were sending thousands of U.S. firefighters to Australia with their blades. 17, Portugal had massive fire. So we're seeing trends in my world among the science community. As lay people, you're seeing headlines that are suggesting that something may be different. You know, in the last 20 years, that's not true. The largest 20 fires in California, if we break it down on a piece of the pie, you know, 4 of those were from 32 to 99. Another 8 or 9 from 2000 to 2019. In the last 2 years, California's had 9 of to talk about today is a little bit of climate and how we, as fire scientists, use climate models to really predict, to make observations on how it's influencing our fire environment and how it may influence our fire environment in the future. I'll talk about burn severity, acres burned, and is it changing? I'll talk a little bit about the fire deficit, which I'll explain, and then really where are we going? What does this mean, and what does our future look like? There is a lot of science in this presentation, but I was under the impression that this was a fire science lecture, so bear with me. Some of it I'll just walk you through, but this is CO2 concentrations in our atmosphere from 1950 to 2000. We see these are observations that are tracked, an increase in CO2 emissions. Where we go from here, we use climate models to predict what is our future concentrations going to look like. Some scenarios in blue would suggest that we may actually level off in a 20 to 30 year period. Extreme conditions in red suggest that we may continue on this upward trend. How we do that is really up to us and up to Mother Nature. There's a lot of things that factor in to where this curve goes. Some includes biomass burning, certainly natural events, solar flares, volcanic eruptions, what we do in industry and how we consume as individuals, how we use our land, all factor in the projection of where this curve is going to go. Regardless, the trend is upward. So we use models like this to give us an idea of what our climate is going to do and how that may impact us as land managers and as stewards and as fire practitioners. So if we're really going to use these types of models, how confident are we in what they are able to do? Pretty hard to see in this light, but there's three curves here. The bottom is a baseline without anthropogenic or human factors, without any forcing. And it would be a zero change in temperature. That's projected along this curve. The gray on either side is just the confidence intervals built into these climate models. There's a lot of variables that are used to feed these climate models. They do ensembles and simulations of thousands and thousands of iterations, and they get a statistical average of what these outlooks might look like. When we factor in human forcing and observe, we see very good alignment with what this data is suggesting with temperature. So that builds confidence, like, wow, this would probably be a good tool to use if we really wanted to use it to predict what our future climate might look like. Sorry, cars that we talking about today. That's not what I keep on. We can look at temperature and precipitation over the last 80 years. From 1950 to 2020, precipitation, and from 1950 to 2020, temperature trends. Again, this is observed data, this is a model. And as you would expect, you see cycles. Those of us that were here in the 80s remember how great the ski seasons were in these early 80s. We also remember the Great Salt Lake flooding, and Governor Banger putting in pumps to move the water from the Great Salt Lake out to the West Desert in the river that ran down Main Street. But we've seen cycles of up and down precip levels. 2020 was an abnormally low precip hot summer. I signal that out because it's going to come up multiple times in my talk tonight. What we don't see, the line here is the mean, the average of this data. So it's really staying constant over an 80-year period of precip. There's highs and lows. It's cyclical, but it's really kind of maintaining that level line. Temperature, on the other hand, we see from 90 on a gradual uptick. It's Kelvin. It's a metric number, but it's basically a degree or 2 Celsius is what we're starting to see in temperature trends. So if we're going to use models to see if this trend is something that's either consistent or an anomaly, we overlay climate models with the same data to see what the trends are showing. Same thing. Kind of precips all over the board. It's kind of maintaining, but we're seeing a gradual rise in temperature. So there's a few indices we use in the world of fire, and one of them is called vapor pressure deficit. VPD. I'll refer to it again. It is really a measure of how thirsty the atmosphere is. It's directly correlated to temperature and precipitation. It's really the difference about how much the atmosphere can hold versus how much it has. If we're atmosphere, where we really see the effects is fuels dried out, vegetation. When I say fuels from a fire perspective, I'm talking about our forests. I'm talking about the grasses, the shrubs, the trees, all are impacted by a changing climate and a changing vapor pressure deficit. We also see greater evaporation of forests, of rivers and reservoirs. And so it's a metrics that we watch closely. And we've been able to track it over, the last, at least the 50s. A lot of this is based on the 50s. I'll show older data. But this is where we started to really see a change in CO2. So we're using this as kind of our baseline. This data, this graph, is a little busy, but this is observations from 1950 to 2000. And it's of vapor pressure deficit and precipitation. We see a pretty good clumping, and it's by year. Dark blue is 1950, up to about 2000 is whitish. We see a clumping, a gathering around 0, 0, which is neutral. That's a really good place to be. We can model that on this data, and we can see that it follows a good bullseye. So the climate is really falling within this boundary. This vapor pressure is consistent. We see highs and lows, maybe an outlier here and there, but it's a bullseye that seems to fit what our climate did from 1950 to 2000. If we overlay from 2000 to 2020, very little of that data fits in that model. In fact, 2020 is an extreme outlier. So maybe we have to look at a different climate to see where this fits.
Stand by.
Okay.
I'm back.
So, again, if we look at 2020, based on that 1950 to 2000 model, that model projects or predicts that we would get a VPD that we saw in 2020 only 2% of the time. And that we would get a VPD of what we saw in 2020, never. So maybe we need to think about a different model. If you rerun this model using 2010 to 2030 projected climate, we now see a bullseye that shifts. And we now get a percentage of about 2% again, we would get that precip, and about 0.5% we would get a VPD of that level. If we run a climate from 2030 to 2050, we see a VPD of about 12%, which is extreme. This might be suggesting that this is the new normal, if this is the projection of where our climate's going. So how does climate, weather, precipitation, humidity factor in fire behavior? Fire really is weather, fuels, and topography. The key indicators with weather is temperature, wind, relative humidity, precipitation. Fuels, gets hot, fuels dry out. Low humidity, fuels dry out, they reach the point of ignition quicker. Relative humidity can add or remove water, so on a wet, damp, moist, dewy morning, it's like fuels are like a sponge, especially fine fuels, grasses and dry fuels, they'll suck up that water, but as the heat of the day increases, those fuels dry out and become receptive to fire. Most of our extreme fire behavior is from 2 in the afternoon until about 6 to 7 at night, when they're in the peak of solar radiation and fuels are really drying out. Temperature rises, RH plummets. The topography and aspect is pretty self-explanatory, right? South-facing slopes, getting a lot of radiant energy, those fuels are drying out. You get diurnal winds, upslope, downslope. North-facing slopes retain water, that's where your heavy timber is, and they don't see as active fire behavior. But all of this plays into our fire prediction models. If you look at national or Western data, I'm sorry, these look much better on my screen. But of the Western regions, from 1984 to 2010, all of these regions are seeing an upward trend in acreage burned. The amount of fire we're seeing on the landscape is more, and the area burned is greater. This is data showing acreage burned over the decades. We're seeing a slow mean as the bar going across. Each decade, we're seeing an increase in acres burned. We're seeing temperature rising during fire season, a couple of degrees from spring to summer. routine, and it goes from an open stand that you could drive a covered wagon through to something you can barely walk through. And that's a buildup of fuels. And now these fuels are drier. Our fire seasons are longer. We're having less precipitation. Our droughts are prolonged. Our VPD deficit is growing. And so we have a fire issue. We've got high severity fire. When you go in and look at this landscape, at the end, there's not much left. There's no seeds. The soil's been impacted. It hasn't lost its ability to be fertile, but maybe you won't get what you had there when vegetation does return. So, how is this happening? Really, I mean, what is the data? More data. It's kind of cool. You don't need to read the axes so much, but look at the trends. The blue dots are from 1984 to 2000. Another metrics that we use in fire is called fuel aridity. It's the amount of moisture that a fuel has in it throughout the fire season. If it's negative, it means it's a wet, cool, high precip season. If it's positive, it correlates really with higher vapor pressure deficit, less precip, prolonged drought, higher temperatures, drier fuels, and the two match up really well. When we have high fuel aridity, we see this is acreage burned on the landscape. Everything in red, and the trend that we're seeing, that upward trend, is suggesting that we are seeing more and more and more fire on the landscape, and larger fire, and more area burned. And then we throw in 2020. 2020 was on record one of the largest fire seasons we've seen in the western U.S. It is an extreme outlier on this plot. If we plot this data against temperature and VPD, these plots are individual observations by year, and again, 2020 suggests that it's an outlier. This is with climate from 1986 to 2015. If we readjust this data against a changing climate with a 2-degree increase in Celsius, 2020 no longer looks like an outlier. It looks like the new normal. Is this where our fire seasons are headed, what we saw in 2020, with a changing climate of 2 degrees C? It's kind of the questions we ask. We can look at, we can model burn probability based on fuel aridity, vapor pressure deficit, relative humidity, temperature, climate, historical observed, and future forecasted. And in red is a higher probability of fire on the landscape. Blue is a lower probability. This is for 1992. This is what this graph looks like forecasted in 2030. But we see a drastic increase in the probability of acres burned with our forecasted climate models. So let's go back in time. We need to look at the past as much as we need to look at the future when we talk about fire on our landscape and what our future might look like. I'm not even going to try and force you to look at this. I'm going to try and read this. This is 1,500 years of data. This is present day going back in time. And in particular, this is data that was taken from lake beds. And it's charcoal deposits. And we can see that this red line is an indication of how much fire was on our landscape over 1,500 years. We see dips and peaks, troughs and valleys of that red line, which is, again, an indicator. It's based on those carbon deposits, we can build and reconstruct our fire history back in time. We can do the same thing with reconstruction climate models. This black dotted line, we use ice cores and deposits that are in the ice and molecules that are in the ice, and we can get an understanding of what our climate was back in time. And it tracks surprisingly well with fire on the landscape. It can pick up events that we know of. A warming period during the medieval. We had a little ice age about 1,000 years ago, 500 years ago. You would expect during the warming period you'd see more fire on the landscape. A cooler, wetter period, you'd see less fire. What we don't understand, or what doesn't make sense, is a split, a deviation in these two curves starting about 100 to 150 years ago, where the climate suggests that we should be getting more fire on the landscape. But the red line is showing we have less. That's what we call the fire deficit. That's when the Forest Service and land managers decided the fire was bad. And we decided that any fire on our landscape needs to be suppressed. And it's a smart, we thought, thing to do. Land barons, timber barons, railroad, mining were rapidly moving west and taking advantage of what our politicians and leaders at the time thought was a national treasure. In 1905, Aldo Leopold, Gifford Pinchot, Teddy Roosevelt formed our national forest system. 200 million acres exist in our national forest system. But the Forest Service, which was created in 1905, then was put in charge of managing. This was a coveted job. These were Yale graduates, these were Princeton graduates. Being a forest ranger was a coveted job. Your sole purpose was to manage your land and prevent fire, and they did it well. The government can get criticized for a lot of things, and I can understand a lot of them. We are 97% effective at putting out fire. Every fire that starts, 97% are put out within a 12 to 24 hour period. Everything that makes the headlines in the news is that 3% that we were unable to contain. What's happened by putting out fire for 120 years? We've changed our landscape. We've allowed an accumulation of fuel. So it's really easy to paint a broad stroke that our climate is changing, and that's why we have these issues. But when, in fact, we, as land managers, have to bear some of the burden of the conundrum that we're in. We can look back in time. The trees tell the story themselves of what the fire intervals used to be. There's study sites throughout the Northwest, but they've since expanded throughout all of the West, throughout the Southeast, where they can go and they've harvested cookies, a piece of tree just like this one. You sand it down and look at the growth rings under a microscope, and you see cracks and fissures in that tree that shows that a fire came through and it wounded that tree, but it didn't kill that tree. And this happens so often that it created a database. We can see just how frequent fires burned in different landscapes, and they were low-intensity fires. They were cleansing. It's like weeding your garden. It puts nutrients in the soil. It opens the canopy. You get some crown fire, but that just allows more UV and germination to occur, and you get the cycle repeats itself. But these were regular, return-interval fires, and our entire Western ecosystem evolved with fire. This data shows that in many of these sites, the average return interval was 7 years. Natural fire, lightning strikes. We know native populations burn on a regular basis for hunting, for travel, for enemies, whatever it may be. I mean, if you want to walk through the forest, it's a lot easier to walk through an open one than a closed one. The reality is, regardless of why it happened and how it happened, it happened. And we've since suppressed it. This is 1880, and this is 1998, 100 years plus. There's not a single scar on this tree to suggest fire was there, when prior to that, the last 15 to 20 years saw fire. This is Northern California, the redwoods somewhere. There's a couple of guys standing right here. This is 1890. Same spot, same picture, same tree still in the background. You wouldn't see a guy standing there if he was there. This is what's happening. We have a massive amount of biomass now on our forests that were not there when fire was in regular intervals. This copy of the poster that I have right here, this is in western Montana, 1909-ish. You can see very open, you can drive a covered wagon through this forest. Over time, from the exact same data picture point, this is now what that forest looks like. What do we do about it? And why is it even an issue? When we had surface fire and a lack of accumulation of fuel, we saw benign fire versus healthy fire. We saw cleansing fire. We saw fire that added nutrients and was really regenerative, positive feedback mechanism. By eliminating fire, we've allowed encroachment. We've not weeded the garden. We have competition. We have invasives. We have things that weren't there that are there. And then they act as ladders. If anyone that's climbed up on a roof, the best way to get there is to climb a ladder. If you're a surface fire and you want to get up to the top, you're going to rely on these ladder fuels, and you're going to climb right from the bottom to the top, and you're not going to have a benign or a cleansing or a regular fire interval. You're going to have a catastrophic standard-placing fire where you drastically change the landscape, and it's hard to recover from. We want to try and reintroduce fire, but how do you do it? We have 200 million of acres of forested land that we're responsible for, we're stewards of. We realize we have a changing climate. You know, is this what we want? Do we want fire like this? Do we want beetle kill? Do we want our forests to look like this? Big patches of beetle kill? We have more trees on our competing for the same or less moisture, the same or less nutrients, drier climate, less atmospheric moisture. Of course it's going to be susceptible. It's like packing all of us into a cage and seeing who's the strongest. Beetles are going to move in and take advantage of that. Fire's going to move in and take advantage of that. It's a kind of a vicious cycle we found ourselves in. So what in the world can we do about it, right? Well, I'm fortunate to be one of the people that get to work in this field. I work at this laboratory right here in Missoula. There's not a lot of us. My colleagues include Canadians, Australians, Japanese, Chinese, Portuguese, Greece. You know, we have international conferences in Portugal, international conferences in California and Australia. But our goal, really, is to face this challenge and come up with processes to solve it, knowing full and well it's not a black and white answer, right? This is a complex issue. And you, as observers, are wondering, is this normal? What is our future, regardless of climate change? Maybe you don't like smoke. When is the Forest Service going to get their crap together and figure this out? Well, the long and short of it is it's going to take us a while. But what, as a homeowner, should you be worried about, right? I work with private and nonprofit groups that are looking at home ignition. This is a large facility in South Carolina that I go to on a regular basis, massive wind tunnel. 140-mile-an-hour winds we can generate. It's bigger than this building. We can bring entire homes into it. This was built to solve and address building codes associated with hurricanes and tornadoes. They've since figured that out. Their big puzzle now is fire. They are spending more than half of their budget just on the fire home ignition. Something that we just saw in Colorado. We just saw a year or two ago in Paradise, California. The car fire. The dude fire. I mean, you can pick a fire name and it's probably got a fatality or a property loss associated with it. And this is our new normal. There's things that are really happening not only in the science world, but in the stakeholder world. Agencies, civil stakeholders, private landowners, community groups. They'll bring in, they can look at community adaptive properties. They can do a risk assessment. They can look at the landscape. They identify those areas that are critically susceptible, that if they go, the neighborhood goes. We look at a fire adaptive community, a fire resilient landscape. All of this, which I love, is based around this little piece right here. There is a lot of science that is going into this. And I'm excited about that. I hope this isn't just a doom and gloom conversation I'm having with you. I hope that there is some optimism that comes out of this, because I love what I do. I'm excited about what we're doing. I'm frightened about some of the trends that we're seeing, but it doesn't mean we're turning our backs. You know, this is Missoula. We have a very aggressive risk assessment community. We have stakeholders, landowners, private timber industry, state and federal. This is basically a graphic showing where our highest areas of risk are and where we would focus the money and the manpower to reduce that risk, so that when, not if, but when fire comes out of this landscape, we're prepared for it. This is happening across the West, but it may or may not be happening fast enough in a town near you. So I bring us back to this forcing future slide. This to me is the crux for you young people out there of where do we go from here. I am fascinated by the different forcing factors that drive our climate. But I'm a consumer. I'm a contributor. We all are. But this is the upward trend the data suggests. And these are the issues that we as a community, myself and the science world, are facing, and the challenges of our national land. So I thank you for your time. I hope that was informative. I would be happy to entertain questions, but I'm going to let John speak first, and then we'll entertain questions together. So.
Is this, I can get the microphone on now? Let me switch slides over. maybe stretch their legs while we're in pause mode.
We have to go back. Wait, then we have 20 minutes.
Really? They came out really wonderful. Well, I sent it out, but still. Yeah.
Is there a reason the laptop may not be speaking to the screen?
Spent $37,000 on it. Yeah. The one we had that had no problem. Constant problems. Can't even read those slides.
Oh, yeah? No more, I guess, huh?
Okay, well, thank you all for being here, and thank you for inviting myself and Dan out for this lecture series. Hopefully I can show up for the next part for the water portion. But I will also be talking about fire in the West. So I'm John Slator. Started my life off here at Jeff Memorial, graduated class of 1991. From there I went to Utah State where I got an associate's degree in archaeology, which are actually a bachelor's degree. See, I don't even use that degree, so I'm not even sure what it's in. A couple other ones as I've moved on in life, but I began my fire career in 1999 with Logan City Fire Department, then to South Salt Lake Fire, and in 2004, I got hired by Unified Fire Authority here in Salt Lake. 2006, paramedic school, and I worked as a paramedic for 13 years on the streets here in the valley from Magna to Snowbird. And then in about 2019, I took over the fire management program for Camp Williams. So Camp Williams contracts with the Unified Fire Authority to provide their wildland fire mitigation. As some of you may remember, 2010 had a machine gun fire, which impacted the city of Harriman. And that kind of led to us getting that contract with Camp Williams. So Camp Williams is a military base. It's located to the west of us here near a town named Bluffdale and between Eagle Mountain. It's 27,000 acres out there, and it's basically a playground for the military. So one of our, the big groups that perform perform out there, the artillery group. So they have artillery, they have hand grenades, all kinds of machine guns. They like to start fires. So they contracted us to kind of help with that. And who would have thought back in 1991 that I would be out there putting out fires at the military starting. So that was me, 1991. Just wide-eyed, not ready for the world out there. We can move past that. So what do? What is wildland firefighting and what does it consist of? So there's a number of different ways that we can go about this. What you see up there is a hand crew operation. Those are generally 20 people lined up with tools, packs on their backs that can weigh upwards of 50 pounds. Working 16-hour shifts in pretty adverse environments, rain, snow. I've been on fires in July and gotten snowed on. I've been in Alaska in August and not gotten snowed on. So what they're doing here is they're creating a fuel break. They're taking that fuel away from what the fire can consume in order to try and put a stop to it. Our hand crews are kind of the background, or the backbone of what we do. We rely on these guys a lot. They're very mobile. They get into places where mechanized equipment cannot, and they really kind of keep everything moving. Another way in which we fight fire is with engines. So I prefer that. It's easier on your feet. You don't have to walk as far. You can drive into fires. But a lot of the places that we have right here on the Wasatch Front, pretty steep area, have a hard time getting an engine up into it. But these typically are four-wheel drive. They carry anywhere from 200 to 800 gallons of water with them, and we can utilize that to put fire out directly. So fire is still not out until we put a tool in the dirt there behind these guys, marching ahead with the water. We do have access to these. You may have seen them this last summer. On the Parley's Canyon fire, we threw a lot of money at that fire through aviation. This right here is about $60,000 coming out of the sky, just each drop. So it's $22,000 an hour to have one of these flying, and then $60,000 for every drop of retardant that they get for us. So again, it can add up pretty fast if you're on a limited budget. So this is kind of what we like to see. You've got a nice cloud cover, it looks like a cool day, it's not super steep, but this is what our hand crews will be going through here in the west. This actually looks like Camp Williams, but it's perfect. The fuels aren't that thick, they're able to kind of pick where they want to make a stop of that fire, where they're going to put that fire break in. You know, they've got the chainsaws out front where they can take out some of those heavier fuels out ahead, and then the diggers will come in behind and scrape all the vegetation down to mineral soil. But unfortunately, this is becoming more of a common occurrence. We don't get to necessarily pick where we want to put that fire out. We can't pick the next ridge over where it might be more favorable. We've got houses, infrastructure, watershed, all things that are being impacted now by fire. We've got more homes on the landscape, and I get it. They put them where it's beautiful, great views, on slopes, with heavy fuel, and nobody wants to cut down a tree because they like the shade. But this is kind of more what we're seeing. This is the Marshall Fire. This took place just outside of Boulder County, Colorado on December 30th of last year. So that part of the country is very similar to us in elevation, aspect, snow load, and the like. And we don't usually see fire in December, and this town definitely saw it. Within a 24-hour period, this fire went 6,000 acres, took out 1,000 homes, and I can't remember the cost. My slides won't show up right now with that. But again, this is something that we're seeing more and more common, where it used to just be, you know, the California fires that we'd see. You'd have those subdivisions tucked away up in the mountains with light flashing fuels all around them, but it's becoming more of a common thing in the West. We've been seeing it in Oregon the last few years, excuse me, and now Colorado. In comparison, it doesn't really show up very well on the map there, but the outline section is the city of Cottonwood Heights. It is roughly the same size as what burned in 24 hours. So it was about 10 square miles and 6,000 acres. I've got a little YouTube video that shows some of that information. If you're familiar with YouTube, you know there'll be probably a commercial that's going to come up. It's usually something good, some solar panels, very applicable for what we're discussing. That vital number was over 1,000. So 100-mile-an-hour winds. I think it was 2 years ago, we had an eastern wind come through Salt Lake. That wind came off the Wasatch, downhill, downslope at 70 miles an hour, and uprooted trees in Liberty Park. It pretty much shut down our cities. We have had crews out fighting fire. You can get engines out there, you can't fly aviation, so you're kind of limited on what we can do as far as a tactical attack on something like that. One of the strategies that we used was to start fires. So we would burn on people's lawns so that that fire, when it came up to those houses in that subdivision, it couldn't get to the homes. So that's one instance where we fight fire with fire. But Dan talked a lot about what we're seeing in our forests. We've got beetle kill, where we don't have those cold, hard freezes in the winter to take out that population. We get large patches of our forest that look like that. We call that dead standing. And that's just a tinderbox out there waiting to be cleaned up. You've got, with the years and years of mitigation with the Forest Service and all the partners, we have all that deadened down. That lumber that's fallen, it's on the ground, ready to be consumed by a nice, slow-moving ground fire. But typically, with that much fuel on the ground, it moves up into the ground, it can really start to move. You look up on the Wasatch at our scrub oak. That scrub oak is now in 10 years of drought. It's susceptible to fire, it's susceptible to vehicles driving by with a chain, with any kind of a spark that can hit that. This slide is full of facts. I like that. Fire season average is lasting 205 days. It's 78 days longer than it was in the 80s. So what's that doing to our crews out there? We're now asking these guys and gals to work an extra 78 days. We like to pay them overtime and get them hazard pay. But there's a price to be paid for that as well. In Utah, we had, on average, 686 human-caused fires. So human-caused fires are unattended campfires. They're those 2 fun days we have, July 4th and July 24th with fireworks. They're driving down the highway, pulling your fifth wheel without your chains. So always check your chains. It's people getting a flat tire and running on a rim. The Parley's Canyon fire was caused from something like that. Then we have natural cause fires. We have less natural cause fires than human cause fires, 417 on average. And this is all within the state of Utah. And our lightning storms here in Utah are kind of sporty. Utah is the second driest state in the nation, with Nevada being the first. But we get these lightning storms come in without precipitation with them, so we call those a dry lightning storm. Those are a little bit easier to manage because we know they're coming. We can look on our apps, on different lightning applications, and see where those fires and those lightning have gone, so we can send out crews to patrol. But we can't cover all the ground that people go into. Especially, you look at 2020, there was 1,163 human-caused fires in Utah. That was at the height of COVID. I thought we were all supposed to be hunkering down in our homes and not going out. Why were people outside in record numbers starting fires that year? One of the questions came up today, does COVID cause fires? And I'd like to say yes, it did. We have tripled the number of acres burned on average over the last 40 years. The Ness Canyon fire in 2020, that was only an 80-acre fire. We evacuated about 6,000 homes on that and cost $1.9 million. The Parley's Canyon fire last year ended up going 541 acres, 10,000 people were evacuated, and we're looking at a cost of $3.1 million, and that wasn't even with the loss of the structure. So, we are out there, we are in the urban interface. Not sure if I could actually give a definition on that, but an urban interface, wildland urban interface, is where people, structures, infrastructure meets those natural fuels that we have on our landscape. So we're moving up into the canyons. We are spreading out, and these areas are more susceptible to fire because of the fuels, because of the vegetation. This is a map of the machine gun fire. Again, this is prior to me working there. I would put it out, but nonetheless, I wasn't there. I wasn't invited. So that started on Camp Williams on the machine gun firing range, and went. Now I'm trying to remember the exact numbers on that one. Just over 4,000 acres. As you can see, we have a predominant south wind here in Utah, and that fire carried up into the community of Harriman. We lost 3 structures off that fire. But the big takeaway from this picture is, that's the footprint of the fire. If you can zoom in a little bit closer and see all that, there are over 200 homes that have now been constructed within that fire scar. And that was just 12 years ago. This is what our Wasatch Front looks like. The area in blue is construction prior to 1980. And I'm colorblind as well. I think that's either red or black. That's new construction. So since 1980, we've seen this much growth along the Wasatch Front. On the left side, up near the top, that's the town of Immigration. When you at the top right-hand side, that's Draper. That's the city we're in right now. And we look at anything basically along Wasatch Boulevard as right there on the urban interface. So Draper has pretty much doubled in size since 1980 and has the majority of it falls into the wildland urban interface. That lower picture is, I think that's Brighton. Yeah, that's Brighton in the town of Alta. So again, where historically, when I first started fighting fire, we didn't have fire in the Uintas, we didn't have fire up our canyons. They were too high elevation, we had too much snowpack, and we just didn't see the fires up there. But now we're seeing these fairly large-scale fires in the Uintas. Went on a fire last year up near the town of Alta, and we're moving up into these areas that historically haven't seen a lot of fire. So what can we do about it? Moving forward, we have a lot of tools in that we're going to be implementing. This is prescribed fire. This is when we choose the area, the time, and where we're going to put fire on the ground. So we really want to start doing more of this. Unfortunately, the smoke in your valley isn't going to go away because if we're not having natural cause or human cause fires, we're going to have prescribed fires, hopefully. So we'll have to go in, thin out a bunch of these areas for fuel because of how heavy they are, but then we can put these fires in and burn off some of the surrounding areas. Every year, if you look to the west, you'll see there's a duck club out by the Great Salt Lake. And they burn all the phragmite out there almost every year to increase and create habitat for ducks. There's a lot of benefits that come from this. With our deer and our elk populations, they really like it when we have these burns and we clean up some of that overgrowth and we create more of a grass component for them. And it also makes our landscape more fire resilient. So a good prescribed fire can buy us close to 10 years on keeping catastrophic fire out. So if we can paint kind of the west here, the mosaic of nice burns, we'll have those in place, that kind of a scar on the ground that the large fires can't move past. This is what a fuels mitigation project looks like. This is some thinning. So as you can see on the left side there, that area is pretty choked out with vegetation. But we send crews in with saws, with mechanized equipment, and we thin that out. Make piles, and every year, if you follow the Forest Service or the like, you'll see that they're burning acres and acres of burn piles every year. So this is what they're doing. They're getting rid of those fuels as natural as we can right now without fire. We're taking them out mechanically and getting all that work done. The problem is we spend most of our money on suppression tactics. We don't spend it on prescribed fire, on fuels mitigation. And hopefully that's going to change, but I think it's going to be a balance that we're going to have to maintain because those large fires aren't going away while we're doing this. So we're going to have to hire our crews on earlier to get them to work on these fuels projects, and we'll have to keep them on later in the season to do the prescribed burning. So all summer long, these guys are going to be out there nationally fighting fire, and then we're going to ask them to do more work when they get back in those shoulder seasons. This is a fire break. One of the really good examples of this is a shoreline trail that goes pretty much along the Wasatch. That has stopped a number of fires in the past. We're moving all the way up into the hills. It can be a mixed use. We use this for recreation, for mountain biking, for running. We can run infrastructure, water, gas lines, that type of thing you'll see through these types of areas. Hope that